Okay, so now next speaker is Rogan. He will tell us about gravitational waves of rolling axion monodromy.
Hi everyone. I would like to thank to the organizers for this nice opportunity to present my talk. So today I will talk about a recent project that I finalized. It's on archive right now. And the focus of this talk will be the production of gravitational waves from alternative sources during inflation that may be present during inflation. And in this context, I will try to introduce a new mechanism that can produce gravitational waves at CMB as well as at interferometer scales. So the last decade or so, we are very well established that the observed density fluctuations are nearly Gaussian, adiabatic, and they exhibit a small red tilt. And initial conditions to generate such properties can be produced by slowly rolling scalar field in its flatten-off potential. And basically, this picture on the left can give rise to the nice plot that we always see in all the talks. So another generic prediction during this simplest paradigm is the production of gravitational waves from the vacuum fluctuations of the metric. And we generically constrain this signal by a tensor to scalar ratio, which is currently should be less than 6% by Planck. By future missions, we are also hoping to improve this bound by an order of magnitude or more. So in the simplest paradigm that I depict, it is generally stated that the observation of B-modes provide us the scale of inflation parameterized by this relation. And it tells us that actually the inflationary scale should be quite high. On the other hand, also the same observations in this context can be considered as a first hint of quantum nature of gravity, namely that the metric is a quantum field. What I would like to sort of revisit in this talk is the validity and scope of these statements highlighted by red. So if you recall Matteo's and Gianmassimo's talks, in principle, we can invalidate some of these results by considering energetic enough field configurations on the right-hand side of the metric fluctuations. For example, if we do that at CMB scales, we can indeed invalidate this result that I showed you. Some of this has been considered in the literature before. Here's a partial list of these ideas. If you are interested, you can always check. So this will be also one of the main discussion in this talk. On the other hand, if we have no sources, then it's the amplification of vacuum fluctuations is not enough to create, for example, signals at interferometer scales. Because during vanilla slow roll inflation, the tensor fluctuations usually exhibit a red tilt. So this is shown by this plot, where I'm plotting the energy density in the gravitational waves with respect to the frequency. So the general prediction is this dashed orange line, which cannot cross any sensitivity line of future interferometer experiments. So one generically needs a blue tilted spectrum, such as shown in this blue line. And an exception to this that we have recently studied actually in single field scenarios is that if one can consider some slow roll violation during inflation. In that case, one can generate a localized blue tilt. This is what we showed in these recent papers. So in terms of alternative mechanisms, axions can be considered as a good resource. It's because the axions generically have an approximate shift symmetry. Here I denote by x right now. As a consequence of this shift symmetry, they're actually light and can roll a significant amount of time. So this actually tells us that they have enough kinetic energy that they can dump their energy into the other sectors. So it's a resourceful dynamo or a reservoir, if you like. On the other hand, these axions, due to the shift symmetry, have, for example, natural couplings to gauge fields where they can dump their kinetic energy into. And we can consider a scenario where this kinetic energy, this reservoir, pumps some energy to the gauge fields, and these gauge fields inversely decay into gravitational fluctuations through this inverse decay. and generate observable gravitational waves. But in the same time, the same gauge fields also give rise to fluctuations in this X sector. So if I identify this axion as the inflaton itself, this case is typically problematic. If we especially insist that the gravitational waves sourced by this alternative mechanism larger than the vacuum gravitational waves. This is shown by recent papers. So instead in this talk, I will focus on another scenario where this axion is a spectator. It lives in a hidden sector coupled to the gauge fields, abelian gauge fields, and they only talk with the inflaton sector gravitationally. And to reduce the effects of the spectator axion, the hidden sector is always a spectator, so only the time evolution of the background is completely controlled by the potential of the inflaton, which can be chosen to be flat enough. So it's in the simplest case, one can consider a slowly rolling spectator field in its flat enough potential, as we will see that such a motion can actually induce production of vector fields. So to see this, we can look at the mode equation for the gauge fields. Generically, this interaction, Chern-Simons interaction between gauge fields and the spectator axion induces a parity breaking term in the effective mass of the gauge fields. This indeed breaks parity for certain modes, and those modes also experience a tachyonic instability. So this production of the gauge fields are generically controlled by this dimensionless ratio, namely the velocity of this field in these units. For larger of this ratio, we have more production. A nice property of this production is also that the energy density contained in these gauge fields gets diluted at late times, which corresponds to the right-hand side in this plot that I'm showing you. This is just the energy density contained per mode for this choice of parameter. At late times on the right-hand side, they gets diluted, and their amplitude is maximal for modes that are approximately the size of the horizon for this ratio, around 1. So the key point is here that the gauge field production is generically sensitive to the velocity of the spectator axion. So now we have these gauge fields. In this model, there is the two ways that they can influence the cosmological correlators. Even though we decouple two sectors as much as possible from each other, inflaton and the hidden sector, there is still some leakage from the gauge fields to the observable sector. So which is there are some stringent bounds on non-Gaussianity for this channel. On the other hand, we are particularly interested in this channel inverse decay of the gauge fields to the one helicity mode of the metric. So if we insist that the second channel is larger than the standard vacuum fluctuations, we generally end up again in problems even in this scenario. So one can only generate observable tensor fluctuations at the order of 10 to the minus 3, 10 to the minus 4 in terms of tensor to scalar ratio. So the key difficulty here is that to generate observable gravitational waves from these sources, one ends up having problems with overproducing density perturbations or scalar fluctuations. And the key point here is that the channel 1, which is the problematic one, is active as long as the second field is rolling. So the mixing between these two sectors are proportional to the velocity of the field. So if the field is rolling too much, it generates a problem generally. So to wear on this, maybe we can consider a localized role of this spectator's field, which I will turn next. So we can exploit the fact that the gauge field production is proportional to sensitive to the field's velocity. We can think that actually this means that the signal one can generate in terms of cosmological correlators is also sensitive to how the field moves in its potential. So for this purpose, I will focus on an axion monodromy type potential, well motivated in string theory constructions, where the potential of this spectator axion has the standard modulatory corrections, non-perturbative corrections, as well as the terms that explicitly break the shift symmetry. So I modified the first term to account for the role of the field to its minimum, which I assume to be at the origin here. So at large field values, actually this term is just a linear term in sigma. So if I consider the these non-perturbative corrections that are sizeable but still subleading, namely in this limit, the potential of this field is modified to this shape given by the orange curve. So we have some cliffs and plateau regions, introduce some cliff and plateau regions in the potential onto the otherwise smooth linear potential. So as we will see, the bumpy ride of the spectator axion in this potential can give rise to the localized signature that we are searching for. For example, during the cliff-like regions, the field will speed up. At those times, the gauge field production will get amplified. And in the plateau regions, it will slow down enormously to switch off the gauge field production again. So to see this, we can look at the evolution of the field velocity profile of the field in this dimensionless units with respect to time. I'm choosing some representative values. It doesn't have any physical meaning. So the evolution of this field within this one bump of its potential is shown like this. So in the cliff-like regions, the field's velocity becomes maximal. And again, when the field encounters a plateau region, its speed slows down an enormous amount. And the role of this field is basically controlled by its mass around its minimum. So the more the field has mass, the faster it rolls, the faster it traverses this bump. So in this case, the gauge field production actually exhibits a scale dependence. So this tachyonic mass will be maximal for modes that exist the horizon when the field's velocity is maximal, when this ratio becomes maximal, which I denote by this dimensionless parameter C. And certain modes will be amplified, and depending on this ratio, basically. So to summarize, the gauge field production in this case is parameterized by these three numbers: the ratio between the wave number to this critical wave number, and the velocity of the field at its maximum, and the mass of the field, which determines how fast the field rolls in these bumps. So now we have these gauge fields. They source the correlators through the channels that I described you earlier, and the correlators actually inherit the similar parametric dependence in terms of the set that I described earlier. So all the phenomenology in this model is just consists of two terms: the standard vacuum fluctuations plus the source contributions. And the vacuum fluctuations are controlled by the dynamics of the inflaton. On the other hand, the source fluctuations that I described are controlled by the motion of this spectator axion and the Abelian gauge fields. And they can be all the phenomenology actually in these source correlators bispectrum and the power spectrum are parameterized by these functions. Their scale dependence, how it depends on the velocity of the field, and its peak, parameterized by these functions here. Another important point here is that the bispectrum is always dominated by the source contributions, because the vacuum ones are always subleading, slow roll suppressed. And another property of these bispectrum is that they are generically maximal for equilateral configurations, which what I will focus next. So when all external momenta equals to each other, these signals peak. So now let's consider a scenario where this roll of the axion is maximal, corresponding to the CMB scales, and let's evaluate all these phenomenology at their respective peaks in terms of wave number to assess the level of gravitational waves we can achieve in this scenario. So the biggest constraints comes from always the scalar non-Gaussianity, for which I will use the equilateral shape in this model and use the 2 sigma limits by Planck 2018. This is shown by these dotted dashed red line, so below which is the allowed parameter space. And here I'm showing you the constant tensor to scalar ratio curves in this model. In the parameter space of the model, which is in the y-axis, is just the inflaton's slow roll parameter, and the velocity of the spectator axion, which controls the particle production. So the specific region of interest is always the right-hand side of this dotted gray line, which is the parameter space where the source contributions dominate over the vacuum ones, which is also visible because for small fields velocity, particle production is less, so that these curves, constant R curves, becomes flat, becomes insensitive to the field's velocity Another interesting point about this model is that actually it also can generate quite a lot of tensor non-Gaussianity, for which I use the standard formulas and show you the target sensitivity that can be reached by a LightBird mission. They're expecting to measure a tensor nonlinearity parameter of order 1, so which corresponds to actually the interesting parameter space that we're interested in. So on top of the observed gravitational waves at CMB scales, we can actually hope to see some tensor non-Gaussianity, which is otherwise not possible from vacuum sources. Another interesting point is that in this, when the sources dominate over the vacuum fluctuations of the metric, so now we modify the standard relation between the tensor to scalar ratio and the scale of inflation parameterized by the Hubble rate. So due to this exponential sensitivity to the velocity of the field at its peak, now we can actually arbitrarily lower the energy scale of inflation by always increasing this velocity of the field and its peak to still get an observable gravitational wave signal. So you can compare this relation with the standard relation that I showed you earlier. Okay. On the other hand, we can also consider another scenario where the spectator field actually traverses multiple wiggles. You can choose suitable initial conditions such that the field rolls from a higher value such that it traverses 2 wiggles before it reaches to its minimum. So we can tune the model parameters such that the peak in the velocity of the field and the particle production becomes maximal where the scales associated with, for example, spatial and ground-based interferometers exist to horizon. So here I'm showing you, for example, 2 examples for the field profile of such a case. Here the time rolls from left to right, 60 folds is the beginning, and the field rolls to its minimum way before the inflation ends. So after the field crosses this line, it should settle to its minimum. So we can tune some model parameters such that the field's velocity peaks at scales that are relevant for example, pulsar timing array and square kilometer array experiments and LISA experiments. In the second scenario, I will talk about the same scenario for the first peak. In the second peak, the peak occurs relevant for advanced LIGO scales. So this is like it can be an interesting scenario where you can have multiple peaks in the gravitational wave signal. So in this case, so at sub-CMB scales, we also have to consider constraints, and the constraints are mostly from primordial black hole abundance. Since we didn't observe any primordial black holes, there are, depending on the mass of the primordial black holes, there are some constraints on the level of power spectrum one can have. So this is shown by this red dashed line. So what I did was to determine the maximal height of the gravitational wave signal, I chose some model parameters for the velocity of the field, such that this bound is saturated by the primordial black hole limits. So on the bottom panel, I'm showing you the corresponding gravitational wave signal in this model. So one can see that actually one can reach observable gravitational waves for both LISA and pulsar timing array and square kilometer array experiments. For the second scenario that I described you earlier, for the advanced LIGO case, it seems like the signal barely overlaps with the 0.5 sensitivity line of the advanced LIGO. As for my conclusions, so B-modes and their properties are expected to be measured by forthcoming experiments. So therefore, it's timely to search for alternative mechanisms that can generate gravitational waves. Here I showed you that the motion of a non-compact axion-like spectator field and its wiggly potential can lead to an efficient production of its gauge fields, which in turn generate gravitational waves that can be parametrically larger than the vacuum fluctuations. So one can basically generate observable gravitational waves with a low scale of inflation and sub-Planckian field excursions. The other interesting properties of this signal, for example, for the tensor signal, is they are actually scale dependent, parity violating, and non-Gaussian. Especially non-Gaussianity is an important tool to distinguish between the vacuum versus non-vacuum nature of gravitational waves. So in this context, also any departure from the standard predictions that we expect from single field inflation, such as scale-free, almost scale-free, parity conserving, and high degree non-Gaussianity gravitational waves. So any departure from this scenario would give us actually information about the energy density contained in the hidden sectors. I also showed you that depending on the initial conditions and model parameters, rolling spectator axion monodromy model that I just introduced can also generate observable gravitational waves at interferometer scales. In this context, visible signal at PTA, SKA, and LISA scales are possible, even for a scenario where you have actually multiple peaks. So that'll be it, actually. Thank you.
Okay, thanks a lot. Questions? So please go on.
Can you hear?
Uh-huh.
Yeah, I want to ask whether you consider the primordial black holes formation in such a scenario, because you say that we haven't observed any primordial black holes, but you may also know that there are some mass windows that there is not any constraints, so primordial black hole can have the same abundance as the dark matter. So,
that is true. Yeah, I haven't considered that possibility, but it's certainly true. For example, if you can see this slide, can you see it?
Yeah.
You can have the peak such that these peaks happen at interesting locations in terms of E-folds, such that one generates primordial black holes that are still not.
Yeah, actually,
can be the totality of dark matter.
I remember it's like 40 EFOs around there. Yeah, you're right. But this PPH limit you drew here, it seems that there is no such kind of a possibility for the mass window for the primordial black hole to be large. So
because
I'm
it's
a little bit
So the reason that's actually this primordial black hole limits are a bit lower than what is usually considered, because in this model, the fluctuations are highly non-Gaussian. So you have to revisit your primordial black hole constraints. So that can actually also reduce the threshold for the primordial black hole.
I see. So you mean that the non-Gaussianity greatly enhance the kind of constraint?
It may enhance, as far as I know.
I see. Thank you.
So that's why the limits are a bit actually lower than the standard Gaussian assumption.
Okay, I see.
Okay, next one is Yvonne.
Yeah, hi. So,
Hi.
what's your assumption for epsilon sigma?
Epsilon sigma.
So you plot epsilon phi. So are you assuming that epsilon sigma is much smaller than epsilon phi? How small?
I don't assume that. No, it's not. There's no any restriction on it actually.
On epsilon sigma, but it has to be at least.
There are some restrictions to it from back reaction constraints actually. Can you see the slide?
Yeah.
So there is some constraints. So for example, the energy density in the gauge fields obviously has to be smaller than its reservoir to keep things under control in terms of back reaction. For example, this constraint is basically proportional to the epsilon sigma that you're talking about. And it turns into a constraint in terms of this physical ratio. And you can always find parameter space where you can still achieve signals at CMB scales. For example, there's another constraint here on the constraint on the right hand side that actually assumes there is for example, in this multi-field model, the spectral index is modified in this way, which we know to be 10⁻². So to avoid fine tunings, accidental cancellations, you may assume that this is, for example, epsilon sigma to be less than 10 to the minus 2. That gives me this conservative bound in terms of physical parameters. So there is actually a constraint on epsilon sigma too. To avoid fine tunings, you may have to assume the epsilon sigma when at its peak has to be less than 10 to the minus 2.
Yes. So if yeah, I'm asking this because so yeah, do you have this constraint on f over m plan, but then so there's 0 psi, you want it to be bigger than this 4 point something that you have. So the smaller epsilon sigma, the larger the smaller also your fraction of f over m plan has to be, but then also the coupling. I mean, I'm wondering how large is the coupling of the axion to
Oh, you mean this parameter?
Your alpha c, yeah, your alpha c.
Yeah, I didn't describe the back reaction constraints in terms of that. They can only appear in this way, as far as I know.
So yeah.
Certainly you can't have it too much, because otherwise you would bump into other issues from back reaction. But probably you can have it order 10 or more for this parameter, for the velocity of the field at its peak in terms of these dimensions ratio.
Okay.
Okay,
yeah.
Thanks. So next one is Nicola.
Yes, okay. Can you hear me?
Yes.
Okay. Now, I just have a comment. I don't know if it can be useful for your analysis. You were mentioning about the FNL non-Gaussianity amplitude from tensors. So actually within Planck we also gave we produced the first constraints, upper limits on the FNL tensor amplitude. So I don't know, because I see that in your analysis you account for, of course, the FNL equilateral on the scalar sector. I don't know, I mean, if it could be useful also to account for these upper limits that we provided on the tensor amplitude on Gaussianity.
Well, you're saying that there should be also a constraint on the tensor non-Gaussianity.
Yeah, and Planck provided some upper limits, actually the first ones on that quantity.
Well, they will be certainly, as far as I can see from this line, there will be away from the region that I am interested in. It should be, the constraint should be much more relaxed than what I'm drawing here.
Yeah, sure.
Is that
true? Larger. Yeah.
So I should expect them to be somewhere here or something.
Yeah, that's for sure. But just to tell you that.
Sure. Yeah, I'm aware of them actually.
Yeah.